In this video, we're going to look at bromine addition to double bonds. Now here I have a simple alkene and a mole of bromine. What's going to happen? Well, before we do that, I'm going to go backwards a little bit. Let's go back to HBr. What would happen here? What would we draw for a mechanism? We'd have the double bond, attack the proton, and we'd kick out the bromide. What's this going to give us? It's going to give us a simple carbocation. You knew that. That was easy. But now let's change it to bromine. What is bromine going to do? Well, the first thing you draw is exactly the same. Is you draw the your initial arrow to one end of the bromine. Okay, then you kick out the other bromide, and what do you get? Well, you get a carbocation, just like you had before. The problem is this isn't quite correct, because these carbocations don't really form this way. The bromine, of course, has a lone pair on it. It has 3 lone pairs. And what actually happens is that this bromine essentially leans over and attacks that carbocation, and it forms what we call bromonium ion, which is this cyclic compound down here. Now, this doesn't really happen in 2 steps. It happens kind of all at once. And so to show this, we have to back off a little bit. Let's come back. Okay, let's come back. And in this initial reaction, we have to draw 2 arrows to the bromine, one coming and one going, because we show the first arrow of the electrons from the alkene attacking the bromide, but then we draw another arrow showing that the bromine lone pair coming back and attacking one of the carbons. It doesn't matter which carbon you choose. The double bond attacks the bromine, one arrow comes back to one of the 2 carbons. And now when you push the magic arrow, you'll see you get to the bromonium ion directly. Now these bromonium ions are quite reactive, and as soon as they form, they're looking for some source of electrons to relieve that positive charge and to open up that rather strange 3-membered ring. Well, do you have a nucleophile around? Yes, you have the bromide that you just kicked out. So what can happen here is that the bromide comes around and it attacks the backside of this 3-membered ring and opens it up. And now, when we push the magic button, what do we get? We're going to get a dibromide. So this reaction works really well with bromine. In fact, bromine is a colored compound. You can have a solution of an alkene, colorless. You just drop in bromine. You see the bromine color go away as it's immediately reacting with the double bonds. Now, other things can happen if you have other nucleophiles around besides the bromide. And indeed, let's get rid of this all and say, well, what happens if we just do this reaction in water? Because if you do this reaction in water, it's the solvent, and there's much more water going to be around than there is bromide anion. So now, if we do this reaction, we simply form the same bromide, but now what's going to happen in the second step is it's going to react with a mole of water. So we go to a mole of water, and well, now we'll have the water come around. I draw it up here, back down, open up that bromine, and we've got our product, which of course you have to lose a proton from, and this is an easy step to do. Just go like this, and lost the water, and form our product. Now these compounds are called bromohydrins, where you have bromine and water adding to the same oxygen. Now, one of the interesting things about this reaction is that the reaction occurs on the back side, which means that if you have some stereochemistry in your compound, let's start here with cyclohexene. Okay, well, if we do cyclohexene and we add bromine. If we add bromine directly, what we're going to get is the compound where one of the bromines, well, let's say add on top, okay? So we'll have one on top, which would have formed the bromonium ion on top, And the other bromine, when it opens, has to come from the backside because it opened up the three-membered ring from the backside. And we can show that mechanistically by just thinking of the geometry of that three-membered ring. So let's go ahead and draw some arrows here. And Oscar has trouble with the stereochemistry, so we have to kind of imagine it a little bit. But bring the arrow back, and then we have the bromide get kicked out. And so there's our bromonium ion, and so it's sitting on top of the ring. Let's say it's on top. I'm going to draw some arrows, some wedges to show that it's on top. And now when this bromide comes in, it's going to attack the bottom of the ring. And when you do that, you'll get the trans geometry. Now again, if you had if you did this with water, the water would become again, the water would have to be trans to the original bromide. So bromine addition is quite fun. You can do it with chlorine. Iodine doesn't work so well because product diiodides are not very stable. But with bromine and chlorine, this is a very nice reaction. Bromine is the best example.